A good time coming here for the last geophysics one. And when I was here, we like to have inter-university exchanges, and we did with Champaign-Urbana. We haven't this semester, but it's great to have Professor Vanderlee from Northwestern University and a student of Professor Park at the University of Chicago here as part of this, and then our industrial people as well. So what I'm going to talk about today is, it sounds kind of complicated, and it sounds it in the title, but it's not really. But it's the reversibility of first arrival travel times using neural net approaches, or sometimes something called physics-informed neural nets. And so here's the outline of my talk. And I'm going to just give a brief overview. That's why I was talking with Andreas Fichtner, this very theoretical about ETH in Europe at the AGU meeting. Didn't seem to know some of this really basic stuff. And I'll talk about that in a minute. I'll talk about using PINs, physics-informed neural networks, to solve for travel times, and at about that level of sophistication. And then I'll give several historical backgrounds that tons of people have investigated this problem over the years, and famous people. Okay, so let's see if I can get that to go. I pushed it back.
So, yeah, it's the third one down.
Okay, let me try it. Does it get stuck here? Okay, hold it. Yeah, maybe set there for a second. Okay, this is just my overview stuff. There are really different ways to solve for travel time. And we even saw a different one, which amazed me, from Omeng, and I don't see Omeng here. We actually solved the full finite difference equations and then picked travel times from it, which I'd never quite seen before. But there's ray methods, which some people have an intuitive notion of. But you can get first arrivals and later arrivals with ray theory. And then there's kind of numerical solutions, which started, 25 years ago, where you just use a numerical solver on an equation called the Eichhorn equation. And then there's these solutions with so-called pins. And 2 and 3 are important. You'd think you just use ray theory, right? But 2 and 3 are important because first arrival travel times provide essential observational data in seismology, including earthquake locations, travel time tomography, and industrial applications as well, because you need to get timetables to do Kirchhoff migration. So we talked about BP using pre-stack, Kirchhoff migration in their technique. They have to build timetables, and they use the Eichhorn equation to do that. So as fundamental ray theory as that, and it's not switching. And here is the Eichhorn equation here. And let me see if I can hold a picture. I'll do it on this one here. And what this says is del T, which is the perpendicular to the travel time surface, is squared is equal to 1 over v squared. And it's about as simple as that. And what this guy, Andreas Fichtner, didn't realize is in 2 steps, I could get the ray equation from that equation. But with John Pedale, a guy many years ago, he basically solved this with a finite difference technique, only for first arrivals. And it got very popular because you can do it really, really fast. And you don't have to worry about multiple arrivals, anything. It just gives the first arrival. And I'll just give an example of this equation because it got popular maybe a decade ago, where you basically take this equation, and if you have a dense array, either with ambient noise or whatever, you can basically see, and some people have seen this, where you can see kind of a wavefront move across array, like with surface waves or whatnot. But if you can get the perpendicular of the travel times, that's del T, and you can relate it to 1 over v, that's the speed, and that's called Eichhorn tomography. And Tianchi Lin at Utah, Victor Tsai, various people have done Eichhorn tomography. And it's kind of a weird way of doing tomography, but it's very popular among certain circles today. Okay, so next slide. Well, if you do want the full solution, you can in 2 steps go from that equation to these equations, which are called the ray equation. And they're in a position of a ray, some position along the ray, and its tangent or vector called the slowness vector, which is really just del T. And you can solve for that. And once you get your ray trajectories by shooting and whatnot, you calculate the travel time as an integration along those rays. And that's great. Okay. But that gives first arrivals and later. Next slide. Okay. The next term of the ray thing is the amplitudes. And that actually is also related to the rays by this so-called geometric spreading J. And so when the rays go apart, the geometric spreading is bigger and the amplitude goes down. When the rays come together, the amplitude goes up. But then you get an interesting case when the rays get tangents to each other, you get so-called caustic points where J is zero and the amplitudes blow up. And again, if you use other techniques like Gaussian beam migration or Mouse-up techniques, it addresses that. But it turns out basis gray method has that as a problem. But for my purposes, caustics are where the travel time surfaces fold back on themselves and become multivariate. Okay, finite difference solutions for this iconal stuff, just directly solved. And for first arrivals only. And this was done by a guy named Vidali in 1988 in Caltech, and improvements by these French guys, and then the so-called upwind finite difference solutions by Venturi and Symes, and then Seppian, some applied mathematicians, to level set methods. That's called the fast marching method. And another mathematician did something called the fast sweeping method. And it turns out it's not just for seismology that they use it for image processing and various kinds of things. So next slide. Race in 2019 essentially figured out how to use neural nets to solve differential equations. And it basically comes on one fact of these neural nets provide so-called universal approximators to solve differential equations. And so the idea is you basically stick the equation, the iconal equation is, you train off literally solving the equation. And once it's trained, you can solve for rays, any source and receiver anywhere in the game almost for free. And recently, I think the Colifon has a paper for global. And I think some other people in some of the national labs have global. Or once you have an Earth model, you want to get the ray from point A to B, literally in millionths of a second. And you want thousands of them. If you're in industry, you want to get timetables in a 3D thing so you can calculate where the reflectors are in Kirchhoff migration. Okay. So again, once you've trained your pin, first arrivals are really fast. Okay, next slide. Okay, this is there are several different variants of this. And it turns out two kind of came out at the same time. Pin, Ike, and ICONET. ICONET is from Caltech for earthquake seismology. And Pin Ike was from a Khalifa at Kaus University in Saudi Arabia, and that's for industrial applications. And as it turns out, I'm following Grubus, and that's in Russia. And that's 2023. And the only reason is I know the second author is a guy named Anton Dukov, who was here for 10 years, working as Martin Hoop's #2 guy here at Purdue, and a really, really smart guy. And as it turns out, they also do in their paper, they do time tests for this, and NES, which is their solver, really outperforms the other ones dramatically. And we have this guy, Kamier, who's the second author of ICONET at Caltech, was for a year in computer science here at Purdue. And then he went and worked at NVIDIA, so he left out. And you can use this pins for solving the wave equation. You can do other things. This is just the icon equation. So you can just see, this is kind of a junky method compared to NEX. Okay, next. Okay, this is getting back to my problem. And I'm going to use these kind of sinusoidal initial wavefronts. And you can think about it as a reflection from a curved interface or something or other. And I'm going to just shoot some rays because I'm a ray network person anyway. And if I do that, and I got two levels here, Z1 and Z2. So here's my initial surface. And I forward propagate it to Z1 just at the caustics point. And you can see that the green line just forward starts having these little discontinuities. And there really isn't a discontinuity. It's flipping back on itself. And if I go to the next level here, it's kind of full-blown folds in the travel. And there's nothing special about it. It just happens. But the iconal equations only give the first arrivals. And in certain computer science visualization, they only want that first. And in seismology, you kind of do two for certain reasons because it's such a fundamental measurement in seismology. So the iconal solvers and the pin solvers only give that. They don't give that first amount. And I'm going to just allude to the fact that if I have all of these guys, I can completely reconstruct this boundary by reversing this whole wavefront. And I'm going to give an example in the next one. And This is, what ray theory does is it solves for the rays, and what I've done is I've put angle in here as well. And then this is along the array with the sinusoidal interface, and then this is propagating. Each one of these lines is a ray. And it turns out if I tilt this in the direction of sine theta, for this example only, then the rays are perfectly straight from the endpoint to the starting phase. And there's a ray that goes from my sinusoidal interface up here and back, and it's perfectly reversible. And it's kind of a half-assed kind of, yeah, I'm gonna be longer. So, okay, next slide. Okay, this is first arrival fronts, and here's the first arrival. Here's the caustic points, and you see the discontinuities in the front. And what I want to do is I want to push that back to reconstruct the first surface. That's the reversibility. And you can see that that and that are not the same. So that's the basic point. You know, once you're past caustic points on first arrival fronts, they are not reversible. Okay, thanks. And this is just to kind of show that, don't worry about this one. This is at where the caustic just formed. Here's the initial surface, the dotted line. Here's the red one is the propagated, and then this is the reverse propagated, the green line. And I do pretty well pre-caustic. But once I get into caustic formation, then the red line is the forward propagated. This is the reverse propagated, which it tries the best it can to get this, but I don't get those low ones. And there's a name for this, it's called wavefront healing. Okay, next slide. Okay, the phenomena is called wavefront healing. It's got a really long history. The sinusoidal could result from a thin zone of heterogeneity or reflection from a curved interface, and you want to push it back to find the interface. And then, but we're going to use pins to solve that. Next slide. Okay, this is an example of comparing an iconal solver with a pin solver. And here's a source with a heterogeneity. Here's a source here, here's a source here. And I'm just saying that I'm doing well with my trend one, but the pin solves at 100 times faster than that. So for example, for industry, they like this because they can calculate their timetables really fast, okay? So this one, I can also put multiple sources in because I can put sources and receivers anywhere in them, okay? And so next slide. And what I'm gonna do is I'm gonna put a whole bank of them here, propagate a first arrival front to a surface here, and then I'm gonna take that surface and push it back here and just allude to the fact that that surface and that surface aren't the same in homogeneous meter. And this just duplicates what I did earlier, but this is with the pin. So this is the initial surface, this is the forward propagated, and this is my attempt to back propagate, and it's not the same because of so-called wavefront healing. Okay, next slide. But the more interesting thing is what happens when I have heterogeneities in here. Then the forward model doesn't look like a wavefront healing, it's more complicated. And surprisingly here, because the forward one of the wavefront here gets kind of pulled back because of this heterogeneity here, I actually do okay, even if I have a complicated propagated wavefront for this case. Next slide. This is one where the wavefront here is kind of a low and a low, and I get an extended caustic surface here, and that's this red curve. And when I back propagate it, I don't, it's not like I'm just getting the high points and not the low points. It's more complicated. And so next slide. And then I can put, you know, whole bunches of heterogeneities, and who cares if the training is exactly the same, okay? And so now I get, if you can kind of see that black one here, that's the red surface here. And I want to take this one and reverse propagate it with the iconal solver with a pin and go back to my reflector, what have you. And again, I don't have enough information. And I'm going to say it's complicated. It's not just wavefront here. Next one. And this is like a lineated zone or something. You can kind of see that little black line here. That's that red one. And I'm trying to back propagate it. And I'm going to say it's not just similar. This red line isn't just wavefront healing. It's something more complicated. Next slide. Okay, in laterally heterogeneous, the concept of wavefront is too simplistic. Nonetheless, after caustic formation, the propagated firsts are not generally reversible. And this has important implications for observed initial arrival travel times, or for industrial applications for initial arrival timetables for Kirchhoff migration. Okay, I'm going to put this into historical comments really quickly. Next slide. Okay, this one is John Claerbout in 1970. After he moved from layered media to laterally heterogeneous media, was really upset from this example. And this was the first example of using finite difference to propagate wavefronts. And here's a sinusoidal front, and it's moving this way. And as the wavefront attempts to heal itself, and that's the ballistic arrival, it jettisons arrivals into the back of thing. And this was actually a rendition of a Claerbout Johnson paper in 1970, which is not a very good figure. But Claerbout redid this with a beautiful animation from like maybe 6-7 years ago, because he used to give these, he's retired, but he gives these little talks online for the troops and the industry, part of the industry, right? Which are kind of fun. Johnson, by the way, is the brother of a guy who was a department head at Purdue, Harvard Johnson, and this is Ansel Johnson. And Ansel's still alive, and he retired from Portland State out of the Pacific Northwest. The Arvid son, the brother of this guy, is Kai Johnson, and he's a geodetics guy at Indiana University. Okay, wait a second. So if we take all these laterally, if we take the first arrival, which is trying to heal itself, and take all these lateral, Claerbout showed he could reverse propagate the wave equation and get the surface back. And so, but you not only need the first arrival, you need all these later. But he said, kind of, if you watch his videos, he said way back in the late 60s, you could take a seismogram here, and it was really complicated. And they were changing in time as the things were shedding arrivals back, and basically kind of sort of gave up. And it motivated him to do kind of 15-degree and 45-degree migration to attempt to respond to just this problem. And that was another 1970. Now, to put this into modern perspective, Alida Lee was the last person who wrote a paper with John Claerbout before he retired, and he is still alive and retired. Okay, so but anyway, you can see that a single seismogram, unless you've got a dense set of seismograms you can play with, are quite complicated. Even in this naive example where there's no heterogeneities, it's just a homogeneous model. Next slide. Well, I'm going to get to Suzanne. Suzanne's advisor was Hus Nowack, and Hus Nowack in the late 90s wrote a paper called Wavefront Healing and Evolution of Seismic Delay Time. And after development of travel time tomography, problems became aware, and I think a German guy, I don't know, might have been from Carlson guy or something, identified this wavefront healing problem for first arrival travel time. And Nowack tried to address it with something called finite frequency tomography. Well, it turns out I was a reviewer of this very first paper. And here is Nowack, right, a reviewer myself, and the editors, but they're challenged us persistently to draw parallels between the theory presented by us and the limitation posed by the ray approximation in the optical literature, which wasn't really quite correct. And in our effort to keep this paper focused and simple, we did not agree that this could be useful, since the relationship is a complex one, and phase always is stepmother view treatment and optics, which really wasn't my critique at all. They had Freeman Gilbert was the other author. So at the time, basically, it's critical, because if you remember in that triplicated area, there are multiple arrivals, but Nowack wanted to use one, and he did a cross correlation between the synthetic and the data all through to attempt to then essentially address the wavefront healing. Also, what they did is they developed kind of a kernel for addressing this called based on the Born approximation. And the Born approximation is perfectly fine in backscatter. It's not so great for forward scattering. But it got very popular in the literature, these so-called banana donut kernels. And I was critical of those, and I still am, because it doesn't accumulate travel. So for example, my lateral heterogeneity problems, the banana kernel would not do so well in back reversing my thing, using that kernel as my function, okay? So let me go to the next slide. Well, as it turns out, here at Purdue, Martin DeHoop, who's the director of applied math, basically didn't like finite frequency and wrote a series of papers, both first mathematics, but Vanderhilst, the department head at MIT, basically showed that his first arrival travel time tomography was just as good as finite frequency, given noisy data, limited data coverage, and inversion and damping approaches. And so it kind of went in the late 2000s, kind of less interest because of this controversy. And I'm going to refer to Suzanne on that a little bit. But it turns out full waveform inversion started to become more popular with Trump and other people. And I'm going to argue both of those suffer from poor station coverage, if there is station, which limits the effectiveness of those approaches. In reflections, I have sufficient data coverage are needed to do both migration and FWI, but recent applications of machine learning can address this. Next slide. I'm gonna just kind of stop on this because I've already gone over. I should emphasize this number 2 here, that reversibility of fronts is in no way similar to reciprocity. I'm not violating reciprocity at all. This is just lack of wavefronts that aren't there, okay, by using. In 3D heterogeneity, for a long enough travel distance, caustic formation becomes dense throughout the medium, and limitations to using first travel time would limit that for many applications, from earthquake locations, travel time to Mars. So I'll just limit it. Okay, thanks, sorry. I'm gonna go over.
You're perfectly on time. You
We
started
started by
5
now.
minutes